Hello guys, welcome to the Innovation Lab. So this is going to be a follow-on to our last video on these boost converters, and the ultimate goal of this video series is to know if we can connect the outputs of two of these non-input output isolated converters in series, and overall if we are able to accomplish this reliably, that means that we can use a system like this to double the output voltage of our boost converter system for those of us who have a need for high voltage application. Alright guys, in the past few weeks we have been conducting a whole lot of follow-on tests on this series DC to DC boost converter concept, with much focus on the transformer method as we talked about. But also we have been conducting other tests on the system, like we decided to conduct an efficiency measurement between the transformer method and the servo power supply method, so that way you guys can have enough information to make a decision which approach that you want to use. For the very final test, we conducted a long duration load testing on the system just to see how the system will perform under load over a long period, and we were able to run a 3-hour test on this system. And what all of this means is that we're not going to be able to show you guys everything in one video because we don't want this video to get super long. So what we're going to do is to focus on the transformer method for this video, and in the next video we show you guys the efficiency measurements and we show you guys the long duration test. Alright my friends, if you're new to our channel, don't forget to subscribe so you get notified when we release that video. Alright guys, let's get started. Alright guys, so this is everything we need to build the transformer powered isolated DC supplies. So let's go ahead and look at what we have here. So going from the left, we have our input power cables, and this cable is going to bring in the 120 volts AC that we need, and it's going to come into the primary winding of our transformers from these white and black power cables, as you can see here. Then going from there, we have our secondary windings that's going to go into our bridge rectifier circuit. So for our bridge rectifiers, we're using this bridge rectifier that I got from Amazon. This is the MDQ 150A-1600 volts. I believe that this part number breaks down to a current rating of 150 amps and the voltage rating of 1600 volts. And for the filter caps, we have our 63 volts by 6800 microfarad capacitor here, and we have the same exact setup, identical setup on both sides. These transformers are exactly identical, and they're going to be able to give us the same exact output voltage. We're going to rectify the output voltage and then connect it to our DC to DC boost converter. Then we connect the DC to DC boost converters in series, then we apply our load. Alright guys, so if you're new to our channel and you're wondering what we're doing here, where we are connecting boost converters in series, so this video series was actually inspired by a lot of the questions and comments that we have received from our YouTube audience, most of whom have a need for higher voltage applications, given that these converters can only go up to 95 volts. So a lot of people have been asking if we can show a way that you can use to connect the outputs of these converters in series. All right. So in the last video, what we did was we showed you guys the 3 methods that you can use to accomplish this. And all of those methods, the one thing that they had in common was that given that these converters are input to output, non-isolated, which means that they share a common ground, the only way that you can be able to connect the outputs of the 2 converters in series is to have isolated input power supplies or input power sources. So in our last video, we showed that there are multiple ways that you can accomplish that. We showed the isolated battery method, where we used 2 individual isolated battery packs, one to drive each DC to DC boost converter. Then we connected the outputs in series. And we did the same exact thing with our servo power supplies, given that they are isolated as well. We used one servo power supply to drive each boost converter, and we still achieved the same result. But before we could get to the transformer method, which is the final test that we needed to conduct, I made a mistake and I overloaded one of the converters, and we had to stop the video there to allow us to repair the converter and come back and make a follow-on test, as I promised you guys. Alright guys, I'm really hoping that things will go smoothly this time around so we can get through all the tests that we have planned. As I mentioned in the first video, there are 2 options that I want to show you guys in this video of how to accomplish this using isolated transformers. The first one is to use 2 identical transformers, as you guys can see here, and then we rectify the outputs of those transformers, and we use the rectified outputs to drive the boost converters. The next transformer option is to really use one single transformer with a center tap configuration. But what we're going to do is to make sure that the 2 windings of the center tap configuration is isolated from each other, and I'm going to show you guys all of that. So that way, instead of having 2 transformers here, you can actually also accomplish this using one single transformer with separate but identical windings on the secondary side of the transformer. Alright guys, let's go ahead and review our test setup so you guys can understand all the components that we have here and what they are going to be doing during the testing. Alright, from the left here we have our power cable here that brings in the 120 volts AC going into the primary winding of our transformers. The primary windings are connected in parallel and the transformers are isolated, so you have the secondary of the first transformer getting rectified and then going to our DC to DC boost converter, and the same exact thing was done on the second system here, transformer, rectifier, filter capacitor, and it goes into our DC to DC boost converter. Now the output of the boost converters are connected in series, and the overall output, which is the high voltage output, now goes into our digital power monitor. All right, so we have our DMMs here. So this DMM is going to be showing us the voltage level going into the first DC to DC boost converter, and the green DMM here is going to show us the output of the first DC to DC boost converter, and the fluke DMM is going to show us the output of the second DC to DC boost converter here. And again, the overall, we're going to see our digital power monitor. We don't have, we only have 3 DMMs here, so we're not able to monitor the input power going into this second DC to DC boost converter. So but what we have here is a current probe that at least we can see some action, we can see what's going on current wise. Alright guys, for the test load, I had to make an entirely new software controlled load stepper, if you may call it. And this is kind of a fun, neat project that, it took me about a few days to build the board and do the coding and get everything to work. And this is really, really fun. It's so satisfying to see how the loads will come in and step in. Yeah, so we're going to be implementing that for this video. We're going to be using it to step in the load. And the reason why we had to build this was because, as you guys saw in the last video, we ran into an issue with our load control module. So, but this is a kind of a little bit of an easier path, because what we're going to be doing here is with this load control module, as you guys can see here. Yeah, so this LED signifies each channel coming in one at a time. And you guys will be able to see this in full display when we are conducting the test. So the first LED there is for channel 1. And so we have channel 1, channel 2, 3, 4, and 5. We kind of added what I call an overload subroutine there. That when you press the button here a couple more times, it will kind of reset the system. Alright guys, the system is simple. So the plan is to bring in a channel at a time, and we can kind of connect whatever load we want on it. I think each channel for this setup can actually handle up to greater than 300 watts. So we have our 300 watts dummy light bulb here that we are using as our load. So we're going to bring that in. Then we step in a 200 watt light bulb. We step in 40, 40, 40. And after that, we kind of take a look at how much load it puts on our system. We can also change those light bulbs and put heavier or bigger wattage light bulbs on there to allow us to increase the load on the system. Alright guys, as you guys know, we always talk about safety, and especially given that this is a high voltage system and we have two sources of high voltages here, or high voltage power on this setup. The first one will be our 120 volt AC coming into the transformer, and as you guys can see, I have everything nicely wrapped up here. There's nothing exposed, so we are safe there. And going from there, we have our 120 volts DC here at the output that goes to our load. And again, everything is, nicely isolated, so we're not going to have any issues there. So as you can see, we're controlling everything from a safe distance, so we're not worried about electrocuting ourselves or, damaging anything. Alright guys, and make sure you wear the right PPE, protect yourself, eye protection, and gloves if you are going to be touching anything that is live. Alright guys, let's get started. Alright guys, we're gonna have to end the video here. I am glad you made it to this point. As you guys have seen, looking at all the tests that we have conducted between this video and the previous video, between the transformer methods and the battery and server power supply methods. So I would say that I am quite amazed at the performance of this system, looking at the output stability, the output voltage regulation under even heavy load. The system regulated very well. That is quite impressive. Alright guys, so looking at the results of the first test that we have conducted on this series boost converter system using the identical transformer method. So what we saw was that under heavy load, the rectified output of each converter was able to supply about 16 volts DC going into each of the DC to DC boost converters, and we also measured an input current level of about 25 amps going into each converter. And on the output side, we measured a system level voltage of 119 volts DC with an output current of 4.30 amps going to our load, and all of that gave us an overall delivered output power of about 512 watts. Looking at the individual output voltage regulation of each of the DC to DC boost converters that make up the series system. So what we saw was that even under a heavy load, converter A was able to maintain an output voltage level of 59.74 volts, while converter B was able to maintain an output voltage level of 58.88 volts. So if you do the math, that gives us an output voltage differential of about 0.86 volts. For the second phase of the testing, we were able to successfully drive the system using one single transformer that used to be a center tap transformer, but we reconfigured it to become what we call the isolated center tap. So basically what that means in a nutshell is that we have two secondary windings that are galvanically isolated from each other, and then we rectify the output and we use each output to drive each of the DC to DC boost converter. So what we were measuring on that one was at heavy load, we were still measuring an input voltage of about 24.5 volts DC going into each DC to DC boost converter with an output current of about 27.73 amps going into each converter. At the output side of the system, we measured an overall system voltage of 118 volts DC at a delivered output current of 7.59 amps maximum, and we were actually able to push the system up to about 900 watts of load on the output. And this is quite impressive. And again, looking at the output voltage regulation of each of the DC to DC boost converters, we saw that converter A maintained an output voltage level of 59.11 volts, while converter B was able to maintain an output voltage level of 57.6 volts, and that gives us a voltage differential of about 1.51 volts. Alright guys, that's really it for this video. I hope you guys had some fun watching this video. I hope you learned something from the video. If you did, don't forget to give us a thumbs up. Don't forget to subscribe to our channel so you see all the following videos and other videos that we're working on. As I mentioned earlier, we just have one more video on this series to complete the series, which will be to show you guys an efficiency comparison between the transformer methods and the server power supply method. Also, we conducted a long duration test on the server power supply method just to show you guys how reliable this system can be, and we were able to push that to about a 3-hour test under heavy load. If you would like to see all of that, don't forget to subscribe so you get notified when we release the video. Alright my friends, I'll see you guys in the next video.